Morning. Welcome to Krishna's classroom. Now we continue to explore the class of measurable functions, and we will just explore the structure of these class of functions, like the properties they satisfy. Okay. So before that, I think it is worthwhile to consolidate what we did last time. Now I have listed on two sides, side by side, the class of measurable functions and the class of topological spaces. I mean the properties, basically the definition and outcome of that. See that they are, because there is a striking similarity between them. That's why we are talking about it. Now, you see that X script M denotes a class of subsets of X, and with the following conditions, namely the set of subsets are not arbitrarily fixed but satisfying certain conditions, namely that X is an element of M. If A is an element of M, then A complement is also an element of M, and if An is a countable collection of elements of M, then their union, countable union of An, is also in M. These are the three conditions that we require M to satisfy. Now, what are the consequences of that? You see that one can easily infer using 2 and 1 together that X complement, which is the empty set, is an element of. So it is not only X is there, but the empty set is also an element of M. Further, we have An, a countable collection in M. Then you see that the intersection of An is also in M. How do we get that? Take intersection of An can be identified as intersection of An complement, or the union of An complement and then the complement of that. Okay. So it is, you take An complement, each An complement is in M because An is in M. So An complement is in M. So it is closed under countable union. Therefore, this set is in M, and its complement is essentially what we are looking forward to, namely the intersection of An. So these are the outcome of this basic attributes to the collection of sets. On the other side, we have a striking parallel with the topological spaces, and it's worthwhile to look at it. X tau is a collection of subsets of X, and the elements of tau are called the open sets. I mean, remember, it's called open sets. Okay, right. Now, the properties of tau are both X and the empty set are elements of tau. Then if AK for k running from 1 to n is in tau, is a finite collection in tau, then their intersection is in tau. That means tau is closed under finite intersections. And if A alpha is, or alpha is some index set, need not be even maybe finite or infinite. It is countable or uncountable, whatever it is. That's an index set. Now, if A alpha is a subcollection of tau, then their union is also in tau. That means the tau is closed under finite intersections and arbitrary unions. These are the terminologies. So finite intersections and arbitrary unions. Difference with measurable classes: script M is closed under countable unions, and for each element its complement is there, from which you can come to the conclusion that it is also closed under countable intersections. Okay. Now, the complement of a topology of an open set is not necessarily in tau. Okay, except in some trivial situations. Now, there is a basic difference between them, but there are a lot of similarities in their structures also. Now, let us see how this propagates further. Now, we are all familiar from the topological spaces what continuous functions are, and let us just recall them. Suppose tau x is a topology put on x, and y tau y is another topological space. These two are topological spaces, and f is a map from x to y. Then f is said to be continuous. F is said to be continuous if the following. That means open sets in Y. That means elements of tau y have their pullback with F, an element of tau x. So this is what you have. This is x. Now I have F from here to here. So this is some open set E belonging to tau y. So this is F inverse of V. So F inverse of V belongs to tau x. So this belongs to so whenever V belongs to tau y, that means every element of the topology of on Y is pulled back to elements of tau x. That is the criteria. Analogously, we can define what are called measurable functions. There again, the domain is the measurable space. That is, XM is called a measurable space, and the range of the functions that we look at is taken as a topology. So this is what you have. You have X now we take a open set here. Its pullback is F inverse of V in X, and this belongs to, it is measurable. So what we require is that F has the property that the pullback of every open set in Y as designated by the topology tau y is a measurable set in X. Okay, then you say the function f is measurable. So this is you can compare these two definitions side by side and see what is happening. This is This is F inverse of V. Here also it is F inverse of V. Here it is V. I mean, on this side everything is the same, but on this side, instead of F inverse of V being in tau x, it is going to be. So this is the scenario. So it runs almost parallel one another. Of course, the concepts are different. Okay. Now, what one can prove further is the following. See, we talk about the composition of functions. Suppose you have three spaces x m, y tau y, and z tau z. Okay, so you have x m, y is the topology of this, and z topology tau z. Okay, and parallelly you have x tau x, y tau y, z. We are familiar with the concept of continuous functions. Okay. Now assume f from x to y is continuous, and then g from y to z is continuous. Together lies H, which is defined as G composition F, which is from x to z is continuous. This is how, so you take two continuous functions, one from x to y and the other one from y to z. Continuity defined with respect to the respective topologies. Okay. Now what we assert is that, see, G composition F, that is H, is well defined. Okay. And this is a map from x to z. What we can say is that if F is continuous, G is continuous, then G composition F, that is designated as H is continuous. Okay, what is the analogous result? The analogous result over here is, that is F from is measurable. G from y to z is continuous. Then this implies H defined as G composition F from mapping x to z is measurable. That means a function from x to y is given. X is a measurable space, y is a topological space. Then you have got the measurability defined. Then from y to z there is a function g given, which is assumed to be continuous. Then G composition F is, that is the composition of a continuous function with a measurable function is measurable. Here the composition of a continuous function with a continuous function is. So these are the corresponding statement, and this is a powerful result. It's very elementary to prove, but it's I'll give a sample of the proof. The proof is very simple. So you have, see the following scenario. I'll just give the gist of the proof. Very easy to conceive this. I mean, these are developed from the requirements that we come across in the study of or in mathematical analysis. To study some problems. So this is a generalization of what you had. I mean, you recall if you had real valued functions with the Lebesgue measure, okay. Sorry, I mean, you had the real line with Lebesgue measure, and you have a measurable function as a continuous function from R to R. Then their composition is a measurable function, and their composition is also a continuous function because R has a topology. If both F and G are continuous, then G composition F is continuous because R has the usual topology. And you see that the speciality of the Lebesgue measure is that, see, all open sets are measurable. Therefore, every element of the topology is usual topology is a Lebesgue measurement. Therefore, it's a larger collection, but in general, it need not be so. Okay, and you can always construct artificially put examples which violate that, and then do the exploration of that. That's very fascinating. Okay. Now you see, this is a very useful theorem, as I said. It's quite easy to see. I mean, for example, I'll just throw the, I said I'll demonstrate. So what is happening is, see, the proof I am demonstrating with and I. This is X. Have measurable, Y thousand. F measurable, G continuous. So this is measurable, this is continuous. These are the assumptions. Then what happens is that you see the continuity of G asserts that take a open set here, an arbitrarily chosen open set, which is an element of tau set, then its pullback is going to be G inverse. If this is the pullback of this is G inverse of this. Now, since G is continuous, G inverse of B is continuous. Now pull it back using F. You get what you call inverse G inverse of G inverse of B is open, and F inverse, the pullback of F inverse, since F is measurable, is an element of F. Therefore, you see that this is essentially G composition F inverse of B. which is in, that means G composition F is measured. Now it is very simple. See, if you just instead of assuming F is measurable and M is a measurable, the collection of a measurable sets, you replace this by tau x, okay, and then you correspondingly you continuity, then you see that the composition of G and F is going to be continuous. Okay. Replaced by a topology tau x, and F is assumed to be continuous. Then H V will get pulled back to G inverse V, which is which is a member of the topology, and F inverse of G inverse of V is going to be an element of the corresponding topology tau x. Therefore, you get this. So you see the proof runs parallel. Okay. So this is just a comparison of these two results. Now we shall use this to further explore the properties of this collection of functions. Okay. So let us first prove a sort of general result which will enable us to explore these results or the properties of measurable class of functions one by one. Yes. Let me first. Right. So let me look at this theorem. Let u comma v be real that means real valued functions defined from x to r, the range is r, and then you have of course the standard topology on r is accepted, and then in the sense of the definition, u and v are assumed to be measurable functions. Let capital phi be a continuous form on R2. The two-dimensional plane. Okay. Now we define just define H to R by phi composition F. Then so a whole class of measurable functions can be constructed by choosing different phi's from R2. Now let us, so this R2 is an intermediary for this purpose. Okay, and see how this is done. Now this is considered as, see, Hx is taken as phi of Fx. Fx is what? Is equal to that is how it is defined. So this is the measurability that we have. So essentially what is happening here, you have now you have an intermediary like this is R. So you see that now what you have is this, it's a real valued map. So it's a map from the real. Okay. So you have now two things, namely that is phi is a continuous function on this. Now this is your F. So phi maps the ordered pair ST to some element in them, and it is assumed to be continuous. We are assuming usual topology on R2. We are assuming usual topology on R2. So with the usual topology, here also usual topology. Then you say that phi composition F is a measurable function. Okay. So what do we get? Okay. So let us start from. So you see that suppose this is the point X, then this is the one that goes to, this is Hx. So H is the composition of students. It is well defined. It is redefined. Sorry. Yeah. They say some message there, so that disturb me. Okay, that doesn't matter. So what you have is to show that this H is a map from X to Xm to R. So you have now for each x, fx is an ordered pair in R2. This is R2. And that is mapped onto some point hx on R2. So what we are asserting is that the map is is a measurable. How do we do this? Okay. So you see that what you have to do is see x this one. Okay. Now you see that this is continuous. That is the map phi is a continuous map. Therefore, by the previous theorem, see if f is measurable, if f is measurable, f is from x to R2, then h is. But what is given is, see, f is constructed out of v. U and v are real measurable functions. So, what is to be shown that if u and v are real measurable, then the function f from R2 to R, the function f from x to R2 defined by is measurable. If you can prove that, then you are done. This is the question that you are asking. If u and v are measurable functions, is this a measurable function? So let us prove that. If you prove, once you prove that, then the previous theorem actually tells you exactly the required result, that h is a measurable function. That's quite easy to prove. Okay. First of all, you observe that let R be an open rectangle which is with sides parallel to, so R is an open in R is an open rectangle in R2 with sides parallel to the coordinate axis. That is the interval I1 is an interval in the x-axis and I2 is an interval in y-axis. So this. Where I1 and I2 are both open. Now what you have is this see, you can immediately see that F inverse of R is equal to U inverse of I1 intersection V inverse of I2. Okay, because U inverse of I1 is going to be this whole subset of R2. And U inverse of so we are pulling back on this. See, I1 cross R and I2 cross R we are taking the pull back. Okay? So you see that in X you get this is therefore this is the set that gets mapped to. So you see that both U inverse of I1 and V inverse of I2 are elements of script M. Why? Because we are assuming both U and V are we are assuming them to be measurable functions. Therefore, they are in it. So you have U inverse of I1 Okay. Now you see that let V be any in R. Then what one gets is that then what we obtain is that V can be written as countable union of sets Ri Ri, I can J here because I am Rj. Rj is essentially Ij, I1j cross I I2j. Okay. Therefore, F inverse of E going to be equal to F inverse of and this turns out to be simply union of we have already shown that F inverse of R is measurable. That's what we have said. F inverse of R is measurable, being the intersection of two measurable sets. Okay. Therefore, what do you get? So you get the countable union of measurable sets is measurable. Therefore, F inverse is measurable. And F inverse of V being the countable union of so for any arbitrary open set V in R2, F inverse of V is a measurable. Okay. What does it mean? It implies one second. So that completes the proof of this. It's a very simple thing with some very elementary set theoretic results related to the union intersection operations and continuous maps and how these unions and intersections behave under continuous mapping. So it gives that. But this is a very basic result. A very basic result in the sense that it's a sort of omnibus result. You can use it to derive several properties of or some of the vital properties of the measurable. That's what we have. Now, one can use 7. which can be used to derive properties of so now we'll just quickly show how this come and how we select the various functions. So so consequences of the above here.